So a bulb is shown here. Okay, you can see a bulb here, and what all things are written on the bulb that is here. So you can see 10 watt and 220 to 240 volt, 50 to 60 hertz, etc. are written on it. So the voltage of the bulb is shown here, 220 to 240 volt. That is the voltage of the bulb. And this is frequency, 50 to 60 hertz frequency. Our AC is having frequency 50 to 60 hertz. And the power of the bulb is shown 10 watt. 10 watt is the power of the bulb. And we are going to explain what is meant by that 10 watt power. 10 watt power. How they got 10 watt. Okay, we know power, we have studied this power is equal to energy by time, and electrical energy, here it is electrical energy consumed. For example, a bulb consumes electrical energy. It converts electrical energy into, bulb convert electrical energy into, children?
Light energy.
Heat energy and
Light.
Light energy, heat energy, light energy. So energy consumed. Some devices deliver energy. For example, this one, the bulb battery deliver energy, generator deliver energy. But some devices, bulb, heater, iron box, etc., consume electrical energy. So in effect, we can tell power is energy by time, energy consumed or delivered. Some devices consume, some devices deliver. So energy consumed or delivered per time, that is known as power. So energy unit is joule, we know. Time unit is second, and joule per second, it is also known as watt. So unit of power is joule per second or watt. Okay. Then we can see some devices and their powers. AC 1000 watts, 1000 joules of energy consumed in 1 second. And TV, you see, 400 joule, TV or fridge. In 1 second, 400 joules of energy it consumes. But mobile phone, less than 5, laptop, 50, etc. Like that, they consume electrical power. Okay. So that is 10 watt, and we can see the explanation. You see.
Looking at these two numbers, let's see if we can figure out what's the power consumed by this bulb. To do that, we'll first recall what current and voltage means. 2 amperes means 2 coulombs per second. This means through any point in the circuit, 2 coulombs of charge are passing by every second. 2 coulombs per second. And what does voltage mean? Volt is joules per coulomb. This means that when a coulomb moves across the bulb from one point to another, it delivers 5 joules of energy to the bulb. So what we know from these two is that for every coulomb that passes by, bulb consumes 5 joules of energy, and in 1 second, 2 coulombs are passing through. So
Teacher, sound on the good
how much energy,
കേൾക്കണില്ലേ?
joules of
Okay.
energy is being consumed by the pump?
അത് മാക്സിമത്തിലാണ് കിടക്കുന്നത്. ടീച്ചർ കാര്യം ചെയ്യാം, ടീച്ചർ എക്സ്പ്ലെയിൻ ചെയ്യാം. ഓക്കെ, ടീച്ചർ എക്സ്പ്ലെയിൻ
Now, if
ചെയ്യാം.
the current was, let's
ഓക്കെ, അതിൽ മാക്സിമം സൗണ്ടിലാണ് കിടക്കുന്നത്. ഓക്കെ, ഐ വിൽ എക്സ്പ്ലെയിൻ. യു ക്യാൻ സി എ ബൾബ് ഹിയർ and a filament. Here a filament is shown here. When current flows through this bulb, suppose 2 ampere current is flowing through that circuit, 2 ampere current. And then 2 ampere current means 2 coulomb per, we know current is charged by time. Current is charge by time. So coulomb by second. So 2 ampere means 2 coulomb of charge is flowing in 1 second. That is 2 ampere current. And the voltage across the bulb is 5 volt. Volt also we know that is energy, work done per coulomb. That is volt, work done per coulomb. That is volt. So 5 joules of energy it consume, this bulb consume 5 joules of energy per coulomb. When 1 coulomb flows through this, it uses or it gives 5 joules of energy, or it convert 5 joules of energy it consume. Understand? 1 coulomb charge flows through this. 1 coulomb charge flows through that. 5 joules of energy is consumed by this bulb. Understand? That is 5 volt means. Here what is the meaning? 2 ampere. 2 coulomb of charge is flowing per second. Just I'll ask a question with this numbers, children. Listen. All of you listen well, then you will get the answer. See, 2 coulomb flows through the bulb in 1 second. Remember, 2 coulomb of charge flows in 1 second. And here, for 1 coulomb, 5 joules of energy is consumed. So, for 2 coulomb, how many joules of energy is consumed per second? 10. Correct. 10 joules. That is calculated here. See, that 10 joules per second. Joules per second is what? So, here, 2 coulomb of charge is flowing per second, and for 1 coulomb 5 joules of energy is consumed. So 2 coulomb will consume how much energy? 10 joules per second. Per second we are calculating 10 joules per second, and joules per second is watt. Joule per second is watt. So that is how we got the power of this bulb. 10 watt. I showed that now bulb it is written 10 watt. So how you got that power? That is by multiplying current into voltage. V into I. See, that's the 2 coulomb per second into 5 joule per coulomb. They multiplied, so coulomb cancel. We are getting joule per second. So by multiplying voltage and current V into I, we are getting the power. So we got a formula for that. Formula for power. Power equal to V into I. That is the power. So got the equation, children? What is the equation for power?
Voltage in time.
Voltage into current. Okay.
Current.
Very important formula. Understood this one, children?
Yes, ma'am.
Okay.
Yes, teacher.
Okay. Then we can see. I'll ask a question. What is the relation for current? Relation for current. Equation for current. Abhinav. Aparna. Equation for current. Aisha, what is equation for current? Aisha. Gautam, what is equation for current? Gautam. No answer. No one is answering. Okay. Jnanaprakash, tell what is equation for current?
Current I is equal to Q by T.
That equation is used here. 2 ampere means 2 coulomb per second. 2 coulomb per second. 5 volt means 5 joule per coulomb. Volt is joule per coulomb. And we calculated the power by multiplying V and I. V into I, that is power. And next we can see heating effect of current. Okay. Another video I will show you. Next, heating effect of electric current we can study, children. What is meant by heating effect of electric current? Children tell, and by that time it will come. What is meant by heating effect of electric current? Gramya, what is heating effect of electric current? Gramya. ഒറ്റ ആള് ആൻസർ പറയാണ്ട് ഇങ്ങനെ ഇരിക്കുക, എന്താ ഇങ്ങനെ ആയാല്? ഗൗതം, ഇതൊക്കെ ചെറിയ ക്ലാസ്സിൽ പഠിച്ചിട്ടുള്ളതാണ്, ഒന്നും കൂടെ ഒന്ന് പഠിക്കുന്നുള്ളൂ. Manu Shankar, what is heating effect of current? നെറ്റ് വരുന്നില്ല, നമുക്ക് നോട്ട്സിൽ കിട്ടി.
Atom in their path, they bounce off of these atoms.
Okay, I will explain. See, here you see current carrying wires, you can see current carrying wires, here you see. And here the wires get heated. When current flows through this wire, the wires get heated. And heating effect we also have seen in other appliances, home appliances. Which are they, children? Heating effect of current seen. Where can you see?
Mix.
Where?
Iron box.
Iron box, okay. Then heater, lab, geyser, etc. Heating effect of electric current is seen. And what is the reason for heating effect? What is the reason for the figure you can see here? See, when electrons flow, we know they collide with the ions, positive ions of the conductor. Ions are not moving and they collide. See, due to the collision, the electron is transferring its energy to the ions. Electron is transferring energy. When it hit, see, when current flows through this wire, potential difference is applied, electron begin to move. We know they move in a direction opposite to the direction of electric field. That all we have seen. And during its motion, what happened? Collision happened. And it is, see, heating effect is due to this collision. When collide, what happened? It transfer its energy to ions. When electron collide, what happened? It transfer its energy to the ions. So that will get heated. When we now during collision, we know energy transfer take place. So that is converted into heat energy. So what is the reason for Joule heating? It is due to the collision of electron and transfer of energy to the ions, positive ions. Okay, and you can see some other equations you can see. See here, voltage, this is a bulb is shown here. Bulb also is heated, we know. First it is heated, then only it emit light. And then it emit light. When it is heated at a very high temperature, it will begin to emit light. So in a bulb, first the current is converted into, electrical energy is converted into heat energy and heat the filament, and then it emit light energy, converted into light energy. So when we apply potential difference, voltage, that means in our house, bulb get energy from where, children? We have given the connection, power connection is given, and in our house where we are getting, from where we are getting the electric power, children? Tell, anyone tell? From where we are getting the electric power in our houses? In all our houses, we are having the electrical energy. From where it comes from? Please tell. From where we are getting? Transformer it reaches. Okay. Then transformer get energy from where? Transformer is only converting that voltage. That voltage is changed, step up, step down, like that. That purpose is done by transformer. Transformer we have to study in detail. One chapter is there, AC. In that we have to study transformer. So transformer is only converting that voltage, step up, step down voltage. That is the purpose of transformer. Transformer from where? The wires you can see, overhead wires, electrical wires on the road and all we can see. And it is bringing the power from where? From where? Anuprakasham? From where we are getting the electric power?
Electric power origin ആണോ? Electric power origin ആണോ?
Yes.
Dam എന്നല്ലേ മാം?
Hydroelectric power station. Dam. Hydroelectric power stations are there. ഇടുക്കി എന്നല്ലേ നമുക്കൊക്കെ കിട്ടുന്നത്? ഇടുക്കി പവർ സ്റ്റേഷൻ ഇല്ലേ? ഹൈഡ്രോ ഇലക്ട്രിക് പവർ സ്റ്റേഷൻ ആണ്. Waterfall on the turbine, and it turned the turbine. Turbine generator is there. Generator എന്ന് പറഞ്ഞാൽ ഒരു coil. That also you have to study in that chapter. Not telling in detail. So you just understand from the generator we are getting the electric power. Idiki power station generator is there. Very high voltage. They send with the help of transformer. They transfer power to different stations. And we are getting in our nearby station also transformer is there. Very high voltage is stepped down to 230 volt, and that voltage is given to the houses, nearby houses. And big factories and all, they need very high voltage. So required voltage is given by the transformer. Transformer is converting that. Whatever voltage is needed, this company need this much voltage, so that is converted into that voltage. Houses need only 230 volt. So that transformer near to our house will transfer high voltage, or the step down the voltage to 230 volt, like that. Okay. So that is the voltage bulb. Across the bulb it is getting the voltage 230 volt, for example. And here suppose when we apply potential difference, we know the current flows. And the power generated or power dissipated, that is calculated power equal to VI. That is, we have calculated that. And the heating effect produced is equal to VI into T. That is the formula. VI we calculated, that is the power, and power into time. That will give the heating effect. Joules heating. And this is having different, this we can write in different forms. According to Ohm's law, V equal to Mehrunisa. What is V according to Ohm's law?
Yes, teacher. V is equal to
V equal to
IR.
IR. So when you substitute V equal to IR here, what is the formula? IR into I.
I square T by R.
T by എങ്ങനെ വരുന്നേ? V equal to IR അല്ലേ? V equal to
I square by RT.
by അല്ല, V equal to I into R. I into R into
Teacher, V is equal to I into R. Teacher, V is equal to V യുടെ വാല്യൂ വെച്ചിട്ടാണോ നോക്കണ്ടേ?
yes. V equal to IR. IR into I എത്ര?
മനസ്സിലായി. I square RT.
Yes. Heat produced is equal to I squared RT. ഇനി another formula, I equal to V by R. I equal to V by R. So V square by R into T, another formula. So three formula, I squared RT, VIT, V square by R into T. Different formula we got for the heating effect. From this same formula we are substituting for V, Ohm's law. V equal to IR, we get one formula. I equal to V by R, we got another formula. So 3 formulas we are getting for the heating effect of electric current. You can see here, heating effect of electric current. VIT, I squared RT, V square by R into T. Okay, children, understood? Okay, okay.
Yes, teacher.
Before we
Okay. Heat produced in a conductor, we have calculated VIT. VIT, V square by R into T, I squared RT. Joule's law in electrical energy. So current, see, heating effect is directly proportional to square of the current, resistance. So resistance more, heating effect will be more, and time for which the current flows. So this is Joule's law of heating effect. See, Joule's found this by doing experiments. Joule's found this formula I squared R. Later only it proved. So the heating effect produced in a conductor is directly proportional to square of the current, resistance of the conductor, and time for which the current flows. H equal to I squared RT. And other formulas we derive substituting for I equal to V by R and all. Okay. Electric power, that also we have calculated. Rate at which work is done by the source of EMF in maintaining electric current through a circuit is called electric power. Rate at which work is done. That means work done by time or energy consumed per time. Rate at which the energy is consumed. Rate at which the work is done. That is the power. And we got the formula for power. That is equal to V into I. Formula for power. T cancel, we get V into I. Or another formula I squared R. Another formula V squared by R. SI unit of electric power is watt. Okay. Then definition of 1 watt of power is given. 1 watt is 1 joule per 1 second. Okay. Commercial unit of electrical energy. What is the commercial unit? 1 kilowatt hour. 1 kilowatt hour is also known as 1 unit of energy. In our electrical bill and all, they will simply tell unit. 1 unit means it is actually 1 kilowatt hour. 1 kilo means 1000. Kilowatt means 1000 watt. Hour, how many seconds? Hour, 3600 seconds. So how we got this number, children? 3.6 into 10 raised to 6 kilo. 1000, 1 kilowatt means 1000 watt. Hour 3600. So 1000 into 3600 second. Understand? 3600. That is why how we got this number 1000 into 3600 second. 3.6 into 10 raised to 6 joules. Efficiency of a source of EMF is defined as the ratio of the output power to the input power. Efficiency relation. Output power to the input power. So these are small things that you should know. Applications of heating effect of current. That is working of electrical appliances like electric heater, electric iron, electric geyser. Geyser purpose you are knowing? Geyser. Geyser. Children, what is the purpose of geyser? Krishna Prabha?
Yes, ma'am.
What is the purpose of geyser?
I don't know.
Geyser is actually in our bathrooms and all, one device will be there. Water heating. One coil will be there inside that, and water get heated. So that is geyser. Heater in kitchen we use heater. Kettle and all heater will be there. That coil. Actually, it is a high resistance coil that get heated when current flows through. Higher the resistance, higher will be the heating effect. So geyser we use in that bathrooms and all to heat water. Okay. In all these devices, nichrome is used as the heating element. Do you know why nichrome is used as the heating element? It is having high resistance and resistivity. It is tensile. It is easily oxidized by oxygen of the air when heated. So all these are the properties of nichrome. Okay. Resistance is inversely proportional to the power. Yes. This property you should know for doing problems and all. At constant voltage, when voltage is constant, resistance is inversely proportional to power. Okay. V square by R, inversely proportional to power. Constant voltage. Then electric, all these are small things. I think you are knowing what is electric fuse, children. In our home we are having fuse. Fuse. അതിന് മിണ്ടൂലല്ലോ ഒരെണ്ണം മിണ്ടൂല ചോദിച്ചു കഴിഞ്ഞാല് അങ്ങനത്തെ കാര്യം ഒരൊറ്റ കുട്ടികൾ മിണ്ടൂല. Gautam, what is the purpose of fuse in our house? Gautam. മിണ്ടാത്തവർക്ക് ഞാൻ അറ്റൻഡൻസ് കൊടുക്കില്ല തന്നെ. Dibangsha, what is the purpose of fuse? Dibangsha.
Teacher, it will break the flow of current.
When?
Thunder.
When?
When power supply goes higher than 220 volt. Power supply cut
off. Okay, that is the purpose of fuse. Yes, correct. Safety device. It is a safety device. When very high current, more than 230 volt comes, that break the circuit. That will melt. That material will melt and break the circuit. Correct answer. So it is the safety device used to protect electrical appliances from strong current. A fuse wire has low, that is why it is having low melting point. So when very high current flows more than 230 volt, what happened? That material melt and break the circuit. So melting point must be very low. Melting point must be very low. But resistance, it will have very high resistance. It is usually made from alloy of tin 63% and lead 37%. Alloy. So fuse material, it is not actually copper wire. We usually take copper wire also, children. But actually the fuse material is not that. It is an alloy made of tin and lead. Tin 63% and lead 37%. It is connected in series with live wire of the circuit. When current exceeds the safety limit, fuse wire melt and break the circuit. Okay. All these things are knowing. Next is the very important part which you have not studied, I think, last year and all. No, 10th standard. This is Kirchhoff laws. The important part comes now. Okay. Other things, power, heating effect, fuse wire, all these are small things, but important. But most important thing is this Kirchhoff law. Kirchhoff, two laws are there. So we know only Ohm's law circuit. Ohm's law is the simplest circuit, electrical circuit. What all things are there in Ohm's law circuit, children? What all things we use in Ohm's law circuit? Please tell. Components used, apparatus used in Ohm's law circuit. Krishna Sri, tell. Ohm's law circuit, what all things we use to tell. Apparatus used in Ohm's law circuit.
Yes, teacher.
Can you tell?
Meter.
Meter.
Voltmeter.
Voltmeter. Rheostat, correct. Then
Key.
Key is there, correct.
Then cell.
cell. Then resistance wire also. Resistance wire.
Yes,
What?
teacher.
Okay, very good. So all these apparatus are there in Ohm's law circuit. Okay, that is the simplest circuit. But you know, many complicated circuits are there. So in such circuit, to calculate the current is not that easy as like Ohm's law. Not calculating the current through the resistor or calculating the voltage across the resistor. Many resistances will be there. So it will not be so easy. We cannot use Ohm's law in that cases. So we have to use these Kirchhoff rules to solve or to find out the current in such circuit. So in order to simplify complicated electric circuit, Kirchhoff put forward two laws. The first law is based on law of conservation of charge, and second law is based on law of conservation of energy. So you can see, so first law is for conservation of charge, second law is for conservation of energy. Okay, we can see first law. First law is very easy. See, here you can see a joint. Circuit's other parts are not shown. Only a joint is many resistances. You see, some current is coming towards, I1 is coming towards. This is a resistor symbol. So through this resistor, I1 is current and it meet at this junction. And through this resistor, I2 current is reaching. Through this one, I3 current is reaching. But here you see, it is moving away from the junction. I4, the current is moving away from the junction. I5 also, the current is moving away from the junction. So many part of the circuit are joining at this point in a junction. This is known as a junction. So this is a junction. Other part of the circuits are not shown. Only that junction is shown and the law is explained. That means some currents are coming towards the junction and some currents are leaving away from the junction. And we can see I1, I2, I3, the current is flowing towards the junction O. And I4 and I5, the current is moving away from the junction. So the rule is, in an electrical circuit, the algebraic sum of the current meeting at any junction is 0. Very simple. In an electrical circuit, the algebraic sum of the current meeting any junction is 0. Algebraic sum, that means the total current, some current are coming towards the junction, some current is leaving away from the junction, but when we take the algebraic sum, that is considered to be 0. How will you take? There is a convention for taking that. Current coming towards the junction is taken positive and current going away from the junction is taken negative. So we can write the equation, children, equation. We can write the equation. See, current coming towards the junction, we are taking positive, I1 plus I2 plus I3, that is taken positive. And current leaving away from the junction is taken negative, minus I4 minus I5. Then we take the sum of that. Sum, I1 plus I2 plus I3 minus I4 minus I5, that is algebraic sum. That is found to be 0. That means I1 plus I2 plus I3 is equal to I4 plus I5. That means whatever current come towards the junction, that will be leaving away from the junction. So these three currents are coming, I1, I2, I3 are coming towards the junction, and that will be flowing through these two junctions, away from the junction, I4 and I5. That sum will be equal to I1 plus I2 plus I3. That is the Kirchhoff junction rule, current rule, and junction first law. It is also termed as first law. Kirchhoff first law, Kirchhoff junction rule, and Kirchhoff current rule. Different names are given to this rule. It is very simple. What is it? Algebraic sum of the current meeting at any junction in an electrical circuit is 0. Algebraic sum of the current meeting at any junction in an electrical circuit is 0. Whatever current coming towards the junction, that is equal to the current leaving at the junction. No current is accumulating here. No accumulation of current. It is not saved there. It's not accumulation. Whatever current comes, that will leave. So that leaves according to the resistance. Okay. So first law we studied now. In an electrical circuit, the algebraic sum of the current meeting at any junction is 0. Muhammad Adil, M.A. Muhammad Adil, what is Kirchhoff first rule? Muhammad Adil. Muhammad Adil. Mandula. Midun Nandakumar, what is first rule? Midun. എല്ലാവരും പറിച്ച് മുടി കിടന്ന് ഉറങ്ങിയിരിക്കുക അതാണ് മിണ്ടാണ്ടിരിക്കുന്നത് മിത്ര വാട്ട് ഈസ് ഫസ്റ്റ് റൂൾ മിത്ര
The sum of the teacher.
ഫസ്റ്റ് റൂൾ
The sum of the current at the junction is their algebraic sum.
സം ഓഫ് ദ കറണ്ട് മീറ്റിംഗ് അറ്റ് ജംഗ്ഷൻ ഈസ് ഓക്കെ ഓക്കെ മൈക്ക് പ്രശ്നമാണ് കേട്ടോ കേൾക്കണില്ല ആളുടെ ആളോട് ചോദിക്കാം നെന വാട്ട് ഈസ് ദ ഫസ്റ്റ് റൂൾ നെന 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 ശ്രീരാഗ് ടെൽ ശ്രീരാഗ് what is first rule Kirchhoff very important rule children Srirag,
Yes, ma'am.
what is first rule
That the algebra
Ah.
of current meeting at any junction is 0.
in an electric circuit varande
In an circuit.
Okay current coming towards the junction is taken Srirag current coming towards the junction is taken as positive or negative കേട്ടില്ല അത് സാഗർ പകുതി കേൾക്കണില്ല സാഗർ കുട്ടികളെ വിളിച്ച് വിളിച്ച് ഒരു കാര്യമില്ല എന്താണ് ഇങ്ങനെ ആയാലും കുട്ടികൾ തമന്ന 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 ഷാജു അപ്പൊ തമന്ന വിചാരിക്കുന്നത് ഷാജു ആണോ ബില്ലുരാജു ആണോ ആരാണോ തമന്ന ഷാജു ഇല്ല തമന്ന ബില്ലുരാജ് വിളിച്ച് സമയം കഴിയാറായി തന്നെ ശ്രീരാഗ് മുഴുവൻ പറഞ്ഞില്ല കറണ്ട് കമ്മിങ് ടുവേഴ്സ് ദ ജംഗ്ഷൻ ഞാൻ തന്നെ പറയാനുള്ളതാണ് ടുവേഴ്സ് ദ ജംഗ്ഷൻ പോസിറ്റീവ് അവേ ഫ്രം ദ ജംഗ്ഷൻ നെഗറ്റീവ് ഓക്കെ algebraic sum of the current meeting at the junction is 0. Next rule we can see. Okay, we have to do problems with this. This is the second rule. Second rule, loop rule, voltage rule, different names are there. Second rule. See, second law, loop rule or voltage rule or law. In any closed loop of an electrical circuit, the algebraic sum of the product of current and resistance of the various branches of the loop is equal to algebraic sum of the EMF of the loop. Algebraic sum of the product of current and resistance, I into R, sigma I into R, algebraic sum, sigma means sum, sigma means sum. Algebraic sum of the product of current and resistance sigma I into R is equal to algebraic sum of the EMF of the loop. That we see in mathematical form is very simple. Sigma IR equal to sigma E. So how will you explain? Algebraic sum of the product. See I into R means it is a product of current and resistance. Algebraic sum of the product of current and resistance is equal to algebraic sum of the EMF. That is the rule. In any closed loop of an electric circuit, closed loop is important. In any closed loop of an electrical circuit, the algebraic sum of the product of current and resistance of the various branches of the loop is equal to algebraic sum of the EMF of the loop. Okay. Rituparna, what is voltage rule? Voltage rule says about voltage. Current rule tells about the current. Okay. What is voltage rule, Rituparna? Rituparna. No answer. Pavitra, tell what is voltage rule? Pavitra.
Yes, teacher.
What is voltage rule?
That in any closed loop, the algebraic sum of product of current and the voltage is equal to EMF, total EMF in the cell.
Okay. Algebraic sum of the EMF in the circuit. Okay, correct. So here we can see a loop. We can see this is a circuit, closed electrical circuit, and we can see here there is a cell of EMF E1 and here two cells are here. Here another cell of EMF E2 and its EMF is different, and you can see different resistances R1, R2, R3. So this is not like Ohm's law. Ohm's law we have taken only one resistance, but here you see three resistances are taken, two cells are taken, and we have to apply this rule here. So voltage rule and current rule all we can apply here. Well, first here we are explaining voltage rule. So here you take this loop. This loop means three loops are there. You can see three loops are here. Suppose we started our motion from here. That means charge is flowing from positive. Current is flowing from positive of the positive terminal of the battery. Current flow, arrow mark is shown away from this. So current flows through this and it can flow along this path. This is one closed path. A, B, C, D, E1. That is one path. Then A, closed path. When from where you start, we should reach there. A itself we should reach. That is one closed path. Another closed path we can take B. See, from here we are starting from here. E2, that means E, B, C, F, E, and R. Another closed path we got. We are starting from positive of the battery as current. Current is flowing from the positive of the battery. Just like that, we started from here. E, from the cell E2, that means E, B, current flow you see, C, F, E, 2, E. This is another closed path. One more closed path is there, bigger one.